Welcome to part 2 of our 3-part lecture on analog-to-digital conversion. This lesson focuses on the fundamentals of analog-to-digital converters. Analog-to-digital converters convert an analog voltage to a digital word. And recall that a digital word is a combination of bits, a combination of zeros and ones. So let's define a few terms. On the analog side, I'm interested in the full-scale voltage range that I want to be able to convert. So I might have some minimum voltage and some maximum voltage, and the difference between those I'll define as my full-scale voltage range. So my VFSR will be equal to my Vmax, the maximum voltage, minus Vmin, the minimum voltage. On the Arduino, for example, this full-scale range might be 5 volts, where the maximum voltage is 5 volts and the minimum is 0. On the digital side, everything is defined in terms of the number of bits in my ADC. So if I have m bits, that'll give me 2 to the m codes or values with which I can represent the analog signal. And my analog to digital converter will be driven based on some clock signal, and that will define my sampling frequency. So delta t will be the time between samples that'll ultimately define the sampling frequency of my ADC. As we mentioned, the ADC is going from a voltage input to a binary output or a binary code. And in an ideal world, I'd have enough codes that I could plot a one-to-one mapping between voltage and my binary output. So this would be an ideal conversion. In reality, however, analog to digital converters, they do have a limited number of outputs based on the available number of bits. And let's take a look at an example where m equals 2, where I have 2 bits in my ADC. To see the real conversion between a voltage and an output code for a 2-bit ADC, let's label our axes. Let's say I have a 4-volt full-scale range, so I'll have 0 to 4 volts on my x-axis. And for 2 bits, I have 4 possible codes or outcomes here. I have 0, 0, 0, 1, 1, 0, and 1, 1. Now the scheme for the analog to digital conversion will depend on the actual ADC that's used, but let's say for this example that when I get to half a volt, I jump up to a binary code of 0.1, I move over, I get to 1.5 volts, I jump up to an output code of 1, 0, over to 2.5, up to 1, 1, and over. So to write this a little bit differently, I have this mapping between my output code and my input voltage. If I'm between 0 and 0.5 volts, I get an output of 0, 0. If my input voltage is between 0.5 volts and 1.5, I get an output of 0, 1. Between 1.5 and 2.5, I get an output of 1, 0. And between an input voltage of 2.5 and 4 volts, I'll get an output code of 1, 1. It's evident then that conversion errors are going to crop up depending on how we divide up the spacing. Let's calculate then the code we might get for a given voltage input to an analog to digital converter. This code will be defined as the fraction of input voltage, Vn over VFSR, multiplied by the total number of codes, so 2 to the m, where m is defining the number of bits available. And there's going to be rounding errors depending on the type of ADC that we're using. The default we're going to use in this class is to round down. So let's go through a quick example. On my Arduino, I have a full-scale range of 5 volts. I have a 10-bit, m equals 10, 10-bit ADC. And let's say my input voltage is 2 volts, and I'm pulling this off some sensor that I'm interested in exploring. The corresponding code is going to be Vin over VFSR, so that'll be 2 divided by 5 times 2 to the m number of bits, so in this case times 2 to the 10. And that'll result in 409.6, and when we round down, our code will be 409. In the same spirit then, given a code measured by the ADC, I can determine an approximate input voltage. This approximate input voltage is defined as this code, output by my ADC, divided by 2 to the m bits. So the fraction of bits that are accounted for by my code, and I'll multiply that by my full-scale range voltage. And just note here that if your full-scale range voltage does not begin at ground, you'll need to account for that DC offset. If we revert back to the previous example, let's call the code 409. So our approximate input voltage will be 409 divided by 2 to the 10, which is 1024, and we'll multiply that by the full scale range of our Arduino, 5 volts. Now this results in a approximate input voltage of 1.997 volts. And you'll note there's about a 3 millivolt error here. So this is the quantization error manifesting itself. And whether or not this is a problem is really dependent on the application. So these conversions are dependent on the type of ADC that is used, and their construction can vary depending on the components used all the way down to the integrated circuit level. The most common ADCs you'll find on microcontrollers are going to be the slope ADC or the SAR ADC, the successive approximation register ADC. The slope ADCs and the dual slope ADCs, which is a version of the slope ADC, they're a very simple implementation. You can actually build these out of discrete components. So as a result, they tend to be inexpensive. However, they are slow. You'll find really to do a conversion for a code is requiring something on the order of milliseconds to perform that conversion. And they're typically low resolution. A typical slope ADC is on the order of 6 to 8 bits. You might find them as high as 13 to 14 bits, but typically somewhere around 6 to 8 is more common. The SAR, or successive approximation register, is another very common ADC. In fact, the microcontroller on your Arduino Uno uses a SAR ADC. They tend to be faster, so you'll see megasamples, 10 megasamples per second type of conversion rates, and they typically have a higher resolution. So 18 bits is not uncommon for a resolution for a SAR ADC. The sigma delta ADCs, they're going to have the highest resolution. So they're going to have the largest density of horizontal lines, the largest density of quanta. And you'll find these upwards of 24-bit in terms of resolution. So if you're doing some fancy audio sampling, let's say, you might want to consider a sigma delta ADC. And then the flash ADC, this is really the fastest analog to digital converter of the common ADCs out there. With the flash ADC, you're getting upwards of 6 gigasamples per second. Unfortunately, you get the speed, but you have a decrease in the resolution. So most of the flash ADCs are really about 8 bits in terms of resolution. So if your application requires really precise timing, the flash ADC is probably a good way to go. All of these ADCs fundamentally perform the same operation. They're taking an analog signal and converting that to a digital word. So the trade here is really between the resolution in terms of bits and the speed in terms of samples per second. And based on your application, you'll have to choose which analog to digital converter is the optimal choice. And finally, a note here, if you read through the Atmega 328 datasheet, you'll find for the Atmega 328P, P being for picopower here, a description of the analog to digital converter. This is a 10-bit successive approximation register, or SAR ADC, and the datasheet has a nice write-up on that ADC if you'd like to read further.